Hi everyone, the authors are from the Future Intelligence Lab at Tsinghua University. I am glad to share our recent work collaborated with SenseTime Research, the name of which is Vehicle Trajectory Recovery on Road Network based on the traffic camera video data. So here is the outline of my today's presentation, which is divided into 5 major parts. So before we go into the details of our methods, I will first introduce the background and the problem formulations. A large-scale system for obtaining fine-grained vehicle trajectories is becoming increasingly important because it lays a solid foundation for a wide range of downstream applications, such as urban traffic optimization, road network profiling, route planning, etc. Traditional methods recover the trajectories from GPS data from apps or coarse-grained traces collected from base stations, which are costly and, most importantly, only cover limited vehicles on the road. Thus, they are not applicable to downstream tasks. Therefore, there is an urgent need to automate the process and develop a more efficient system for a full amount vehicle trajectory recovery via more accessible data. Meanwhile, with the possibility of traffic cameras installed at the road intersection in the developed cities, we can conveniently collect large-scale video or image data of the vehicles on a daily basis. This unstoppable train inspires us to find a new path, which is to recover the vehicle trajectories on the road network by leveraging the large-scale video or image data collected by the traffic cameras. In summary, we aim at making good use of the easily accessible large-scale video data collected by the traffic cameras to recover the vehicle trajectories, thus exploring the utilization rate of the large-scale camera video data and developing an efficient system for various downstream applications. A direct approach is to propose a general system which is divided into the visual module and spatial-temporal recovery module. Specifically, given the input camera video data, we first extract visual features and develop a clustering algorithm to get the vehicle clusters. Then, the original vehicle clusters are regarded at the trajectory points and are fed into the spatial-temporal module for recovery on the road network. Finally, the recovered trajectories as well as the vehicle clusters are delivered to various downstream applications, including intelligent traffic signal control and road network profiling, etc. However, there are various challenges lying in the trajectory recovery problem, including the incompleteness of the camera network, unbalanced temporal and spatial distribution of the images, and the unbalanced quality of the captured image records. These challenges pose a negative influence on the results of the vehicle clusters. For example, one cluster might include records belonging to another vehicle. Also, records belonging to the same vehicle might be scattered in different clusters. These unavoidable noise and missing might further lower the performance of the recovery tasks, leading to poor performance in the following downstream applications. So here comes the key motivation of this paper. The key motivation here is that two tasks can bring performance gain to each other. On one hand, the vehicle clustering task offers essential discrete points for recovery. More accurate clustering results improve the recovery of the trajectories. On the other hand, the recovered trajectories on the road network are reasonable in terms of the spatial and temporal perspective in nature, which could help revise the initial clustering results that only consider the visual information from the images. Therefore, an intuitive way is to explicitly leverage the recovered trajectory to denoise and complement the vehicle clusters. So based on the motivation mentioned before, we propose the overall pipeline, which is displayed in this figure. It can be divided into 3 major components, including the visual module, spatial-temporal module, and visual ST module. The raw input data sources include the road network and vehicle camera records. First of all, the input road network is converted to a simplified road network covering all camera locations and neighboring road intersections to incorporate the special constraints to the vehicle trajectory recovery. Then we extract multiple visual features from the video data, which are then fed into the multimodal clustering model to generate the initial vehicle clusters. We leverage the vehicle clusters to recover the trajectory on the road network by an HMM method. After that, we design a visual ST module where the recovered trajectories are utilized to denoise and complement the upstream clustering outputs, and the updated clustering results are recovered to be continuous trajectories on the road network again, back and forth. Finally, the outputs of our system, including the recovered vehicle trajectories on the road network, as well as the vehicle clusters, are fed into various downstream applications. We will introduce the details of different parts of our system in the following sections. Given the initial video data collected by the cameras, we first extract visual features by adopting standard models, including vehicle features and plate features. In detail, we use the method proposed by a previous classical model as our baseline results. In the vehicle feature extraction training phase, we use ResNet 50 as the backbone model. Now we have the visual features extracted from the images. We aim at clustering the vehicle records that belong to the same vehicle. The output of these clustering algorithm is a list of candidate images ranked by the corresponding similarity scores. First of all, we use the size similarity to calculate the visual similarity between two vehicles. We use the similarity of car plate features and vehicle features to search the top K record of given images. We further consider the similarity between car plate OCR features in the fine search state to get a visual similarity computed as the formula. We take a cluster with the highest joint visual similarity among the fine search results with a given image and judge whether the joint similarity is greater than the empirical threshold. If it is greater than the threshold, it is considered that it should be included in the given cluster. Otherwise, the image is considered to be involved into a new cluster. Through the above steps, the images are clustered where we hope records belong to the same vehicle would gather together into one vehicle. Now we've got the clustering results where each cluster is a list of candidate images ranked by the corresponding similarity scores. Now we are going to recover the trajectories based on the clustering results. Considering the requirements of actual business applications for algorithm efficiency, here we adopt a classical yet efficient map matching algorithm, HMM. The sense of this algorithm is to utilize a hidden Markov model to find the most probable path on the road network represented by a time-stepped sequence of latitude and longitude pairs. Besides, considering the discontinuity of the output hidden states, we adopt the shortest path recovery to smooth the disconnected pairs on the road network. As we have mentioned before, the key motivation of our work is that vehicle clustering and trajectory recovery can bring performance gain to each other. On one hand, the vehicle clustering task offers essential discrete points for recovery. More accurate clustering results improve the recovery of the trajectories. On the other hand, the trajectories on the road network are reasonable in terms of spatial and temporal perspective in nature, which could help revise the initial clustering results that only consider the visual information from images. Therefore, we propose the visual ST module, which combines the visual module and ST module, which is also dubbed as the feedback module. Furthermore, we divide this module into two parts, the complement part and the denoise part. The first part is the complement module. As we have mentioned before, we have found in practice that some records might be missing in the clustering result, which means records belonging to the same vehicle might be scattered in different clusters. Therefore, our goal is to record the missing record from other vehicle clusters. And in practice, we have observed that the most scattered cases are isolated records which are self-contained in a cluster. Generally, we record the candidates of the clusters by visual features, and then investigate whether the candidates meet the spatial-temporal constraints which indicate that these clusters might belong to the same vehicle. For example, we set the threshold to judge whether the two clusters are driving at closing time periods and closing spatial areas. The second part is the denoise module. As is displayed in the figure, some vehicle clusters might contain records belonging to other vehicles that have ambiguous visual features which might get worse after the previous step. However, we can easily denoise some of the noisy points by leveraging the trajectory level information from the recovered trajectories. Based on this intuition, after merging clusters and recalling missing points from other clusters, we update the latest vehicle clusters according to the recovered trajectories. The intuition here is that we tend to denoise the points which are far away from the recovered trajectories. Specifically, each recovered point can be mapped into a road intersection I, and we multiply the initial confidence score S of each record in the given cluster by the normalized spatial coefficient and get the updated confidence score, where S represents the initial confidence score of each record in the given cluster, which numerically equals the joint similarity between the record and the related cluster center. And the distance between R and I represents the geological distance between record R and road intersection I. Noted that the road intersection here is the nearest one to the given record chosen from the record recovered trajectories. Finally, we adopt an empirical threshold to filter out the records below the requirement. In this way, we can penalize and denoise records that do not meet the special constraints on the road network. After going through the feedback module, we have updated vehicle clusters, which are then fed into the spatial-temporal module again for trajectory recovery. We repeat the above procedures until meeting the stop criterion, which is the number of iterations. For baseline, we choose the traditional VID methods and the traditional recovery methods, and we adopt the most classical and commonly used evaluation matrix in the clustering and recovery task respectively. And here are the overall results for both the vehicle clustering task and the trajectory recovery task. Our methods achieve the best performance. Besides, our approach achieves better performance gain in a larger dataset. We also conduct an ablation study to examine the effectiveness of our designs, and we found that by removing any of the components results in a certain level of performance decrease, which demonstrates the effectiveness of our design. Generally, we combine the visual and spatial temporal module together to boost the mutual performance. Therefore, it is essential to investigate some vital parameters that could influence the results of the vehicle clusters and trajectories. This case study has proved that the recovered trajectory could bring spatial and temporal constraints to the initial clustering result, therefore achieving the goal of refining the cluster with higher recall and precision scores. Finally, we display some of the final results output by our system for downstream applications. So to conclude, one of the interesting findings of the paper is by leveraging the images captured by the traffic cameras, we can recover the trajectories at the granularity of the road intersection, which brings benefits to a wide range of downstream applications. Secondly, the visual information learned by the vehicle clustering task and the trajectory level spatial-temporal information learned by the trajectory recovery task can promote each other. And thirdly, extensive experiments on a collected large-scale real-world datasets has shown that our proposed methods outperforms the baselines. In terms of the future work, we open our dataset and call for more attention to the vehicle trajectory recovery problem. And of course, our work has some limitations now. It is necessary to automate the process of implementing the 3 modules proposed in our work. Also, the current approach about how the trajectory level information could feedback the visual information should be further improved. That's all for our presentation, and thanks for listening.